Okay, I will start the class now. Okay, today's lectures I will continue with floor plan. Okay, floor plan, this topic is one of the important topic. Okay, try to pay attention to the lecture. Okay, floor plan is one of the important steps in VLSI physical design. Okay, physical design is one of the design step in VLSI design flow. Okay, to help you to recall back in VLSI design flow, there is different levels of design. Okay, for the chip. Okay, the VLSI flow that I mentioned before is this one. Okay, this is the VLSI design flow in chapter 1. Okay, there are a few steps. Okay, before physical design, there is architectural design, functional design, logic design, circuit design. Okay, so floor plan is under physical design. Okay, this floor plan will determine the quality of the chip and how the chip is implemented. Okay, and then what is it about floor plan? I will cover further today. And in floor plan, it involves placement and signal route. Okay, all this process, placement and signal routing, I will cover. Okay, for clock tree synthesis, this one I will not mention on this. Okay, I will emphasize on placement and signal routing. Okay, and then other than that, the timing closure, okay, also part of the process under physical design. Okay, but this one I also will not cover. Okay, timing closure will also not be covered. Okay, just this is for you to take note. What are the process under physical design and uh, why floor plan is under physical design. Okay, so now I goes back to floor plan. Okay, this slide is for you to revise back uh, about the processes in physical design. Okay, this one is the similar one with the one that I show you just now. Okay, except that this synthesis, okay, is this synthesis replace the partitioning, and the floor planning. Okay, so you need to remember that this synthesis is about partitionings and floor planning. Okay, and others like placement, clock tree synthesis, signal routing, timing closure is all the same with the one that I show you in the VLSI design flow. Okay, and then this flow chart is a more specific one that describe what is done in placement and routing. Okay, and then here the output. Okay, this flow chart does not include the clock tree synthesis and timing closure. Okay, um, okay, so this one will be emphasized, okay, in today's lecture. Okay, what is a floor plan? Okay, according to this slide, floor plan is one critical and important step in physical design. Quality of the chip and design implementations depends on how good is the floor plan. Okay, the floor plan estimates the area of major units in the chip and define their relative placement. The floor plan is essential to determine whether a proposed design will fit in the chip area budgeted and to estimate wiring lengths and wiring congestions. So an initial floor plan should be prepared as soon as the logic is loosely defined. Okay, the floor plan as you see from the slide given, it is the floor plan of the chip. Okay, it is not the floor plan of any rooms or buildings. Okay, so this floor plan is mean by the floor plan of the chip. Okay, for the floor plan of the chip, there are some criteria that we need to fulfill. Okay, and then there are also some others objective to achieve when we want to create a floor plan for the chip. Okay, so about the floor plan, we can actually arrange or we can optimize the use of the area on the chip. Okay, the use of the area is to place the macro or the blocks. Okay, and then we need to divide the space, uh, divide the space or the area to be placed with the macros or blocks, and also we need to make sure that the space is not occupied. Okay, not a big the we need to optimize the use of the area, okay, for the placements of the cell, macro, blocks, or the input-output pad. Okay, so later you will see what are the elements in the floor plan. Okay, and okay, now you see in this slide, it is about sliceable floor plan. Okay, this is means by a floor plan that may be defined recursively as described. Okay, a floor plan that consists of a single rectangular block is sliceable. Okay, so you see this figure, this is a block. Okay, it does not look like a rectangular. Okay, it looks like a square box. Okay, this one we can assume that this is a rectangular block, but it's not really a rectangular. Okay, and then this rectangular block, it is a single block that and it is a sliceable. Okay, why sliceable? Because you see that when it is partitions, okay, when we slice it, okay, it can be made with different blocks. Okay, if a block from a sliceable floor plan is cut in two by a vertical or horizontal line, the resulting floor plan is sliceable. Okay, so this is mean that this block, a single block, when it is cut in vertical or in horizontal, we can actually slice the floor plan to multiple blocks. Okay, in the floor plan, okay, some of the elements, okay, are standard cells, RAM, and data path. Okay, all these are actually represented in cell, okay, or in blocks or macro. Okay, the blocks can be of varying functions, size, and shape. Okay, there are other possibilities of floor plan. Okay, as you see in this figure, okay, this figure has two block in a floor plan and also three block in a floor plan. Okay, the blocks can be made verticals or horizontal. Okay, so you see this, the pattern of the blocks, the arrangements of the block in the floor plan. Okay, there are different types of floor plan. This is shows the types of the floor plan techniques. Okay, a butted floor plan, okay, non-abutted floor plan, mix of both. Okay, abutted here means that the block, they are touching each other. Okay, blocks are touching each other. Okay, non-abutted means that the block is not touching each other. Okay, mix of both means that the floor plan that has block that touch each other and also does not touch each other. Okay, to illustrate that, you can see this diagram here. For a butted, you see the blocks. This is the blocks. Okay, all of them are adjacent to each other. They are touched to each other. Okay, for non-abutted block, okay, these two blocks, all the blocks here, they are also adjacent, but they are not touching each other. Okay, so this is how we differentiate. Okay, and then for mix floor chart, okay, you see block 1 and block 2, this is they touching, okay, they are touching, and then block 3, 4, and 5, they are not touching. So means that these floor plans consist of abutted floor plan and non-abutted floor plan. So that's why it is called as mix of both. Okay. Okay, so for a button floor plan, it means the channels less placements of blocks. Okay, not a button floor plan, channel space placements of blocks. And then mix of both means partially abutted with some channels. Okay, the channels here, we can understand it as this part. Channels means this is the channel. Okay, this is the channel. Okay, for non-abutted, you see this is called as a channel-based placements of block. So they are channel. Okay, and then for mix, partially abutted with some channel. So only some channel. Okay, so this is how we should understand the floor plan. Okay, there are a few of the objective of floor plan. Okay, why we need to use floor plan? Okay, there are some of the objective. Okay, the objective of the floor plan explain why we need to use floor plan to design the chip. Okay, this is after we have the layout design, we get the standard cells. All the standard cells contains all the logic gates. Okay, they will be used in floor plan. Okay, so in the floor plan, the objective to achieve are minimize the area. Okay, the area means the core area. Okay, it can be the core area. Okay, and minimize the timing, reduce the wire length, making routing easy. reduce the IR drop. Okay, IR drop mean the voltage drop or the electrical potentials drop. Okay, these are the five objectives that to be achieved in floor plan. Okay, floor plan, we can label some of the floor plan as bad floor plan and some with good floor plan. Okay, the good floor plan means that it has a more organized design. Okay, more organized design, and also they achieve five of these objectives. Okay, other than that, okay, to create the floor plan, okay, there are some input. Okay, some input that we must have to create the floor plan. Okay, and these are the input. Okay, that is to be used for the floor plan. Okay, and the inputs here as listed are the synthesized netlist, design constraint, physical partitionings informations of the design, input output placement file, macro placement file, floor planning control parameters. As for the output, okay, the output is the outcome, okay, that are expected from the floor plan. Okay, it determines the quality of the design of the chip. Okay, so the output here, as you see, there are a few. Uh, okay, here listed with a seven output. Okay, and they are die or core size estimation. Okay, macro blocks placement. Okay, input output block placement, row creations, placement blockage, power grid design, and power pre-routing, standard cells placement areas. Okay, so these are the output that we have to know. Okay, we have to know, and then it should be considered. Okay, when we do the floor planning. Okay, so for this core size estimations, blocks placement, input output port placement, power grid design, power pre-routing, standard cell placements area. These five output, okay, I will mention further. Okay, except a row creation. Okay, row creations can be part of others. Okay, the blocks placement. Okay, except the placement blockage. This one I will not be covered in the lecture. Okay, others I will cover today. Okay, and then as you see this figure, okay, this figure show you the real floor plan. Okay, the elements here, as you see that they are macro. This is the macro. Okay, and then there are power and ground straps. Okay, you see the line in green color and the red color. Okay, all these are the power and ground straps. Okay, sometimes we also call power and ground routing. Okay, and then corner cell. Corner cells means this part. Okay, it is at the corner. So there are four corner here. So this four corner we call it as corner cells. And then standard cells. Okay, standard cells is actually this one. Okay, the middle one. Okay, all these are standard cells. And then VDD and VSS rails. Okay, all these are like buses. Okay, they are they are actually to connect to the straps. Okay, if I'm not mistaken. Okay, if according to this drawing. Okay, and then here the side one is the input output pads. Okay. Okay, about floor planning. It is the process involved placing blocks of macros in the chip or core area, thereby determining the routing's area between them. Floor plan determines the size of die and creates wire tracks for placements of standard cells. It creates power ground connections. It also determines the input-output pins or pad placements informations. Okay, when we consider the floor planning, okay, one of the output that we should consider is the area estimations. Okay, so when we do the area estimations, we need to do planning on the area. Okay, so this slide is about planning and estimations of the chip area. Okay, which one is the core area? Okay, according to this figure, as you see, this is a floor plan of a chip. Okay, the core area is actually in the middle. So this is the core. Okay, this is the core. Okay, and others like this one, this is the blue line. This is let me see. This is actually the ground strap. Okay, this is ground strap. Is if you refer to this one, it already indicate. Okay, this is the ground. Okay, this is power. Okay, this one power. This is ground. Okay, and others. Okay, like this one. This one is corner cells. Okay, is similar to the one in previous. Okay, and others like this one. This one is input output pad. Okay, input output pad. Okay, so when we want to estimate the core area, we have to consider um, the cells and macros that to be placed in the core area. Okay, we want to make fully use of the area in the core. Okay, okay, how to fully use it? Then we have to arrange the macro and the standard cell. Okay, in appropriate way or in an optimized way. Okay, okay, they are some of the examples later which will be shown to you. You can see how to estimate. Um, okay, and not really estimate, but to show you how the arrangement can be done. Okay, about core and pad limited floor plan. This is about the area. Okay, the area different occupied area. Okay, in different floor plan. Okay, this one there are two different floor plan. Okay, one is with a large core area. Okay, another is with limited core area. Okay, so this is the difference. The core area we can actually determine ourselves when we do the floor planning. Okay, floor plan control parameters. Okay, if we want to estimate the core area, then we need to know what is the measurement and how do we determine the measurement and the measure unit. Okay, when we want to measure the core area, uh, there is a unit. It's not a unit, sorry, it is a term. Okay, uh, core area depends upon aspect ratio. Okay, the aspect ratio is defined by height over width. Okay, it design the size and shape of the chip It is the ratios between horizontal routing resources to vertical routing resources, ratios of height and width. Okay, I see some of the website, the aspect ratios is height over width. Some they mention is width over height. I didn't have time to verify that. Okay, aspect ratio, as I remember, it should be width over height. So this one is I refer to one of the website. Okay, you may have to verify yourself. Okay, aspect ratio. Okay, but according to this, the aspect ratios, the measurements given here is height over width. Okay, if we see the figure given here, okay, assumes that all these are the core area. Okay, we core area with different dimensions, and this core area they are having a different aspect ratio. Okay, we can determine the aspect ratios if we know the height and width. Okay, with the use of this formula. Okay, so for this one, directly we know the aspect ratio is 1. Okay, because the height is x, width is x, they are the same. So aspect ratio is 1. Then, and aspect ratios for this one, okay, the height is 2x over x. Okay, so the aspect ratio is 2, and this one is 1 over 2, means 0.5. Okay, when we estimate the area, we want to make sure that the area that uh, the area that we estimate should be occupied, okay, with cells and blocks. Okay, so we don't want to waste the area. Okay, the area that to be used in the chip, the core area, we want to make that to make sure that they are fully occupied or fully used, okay, or fully utilized. Okay, so core estimation is quite important. Okay, it is quite important because we need to make sure that the area is not wasted. Okay, so after we estimate the area, we need to plan the core utilization. Okay, it defines the area occupied by the standard cells, macros, and blockages. Okay, this is blockages and core utilizations. Okay, how do we determine core utilizations? This is the formula is given. Area of the standard cells and the macro and the pets divide by total core area. Okay, this is a formula that we can use to know the core utilizations. If the core utilizations is 0.8 or in other means 80%, okay, it means 80% of the core area is used for placing the standard cell, macros, and other cells, and the remaining 20% is for routing purposes. Okay, so this is the reason why the area need to estimate. Okay, and then with the core utilizations. Okay, okay, macro blocks placement. Macros may be memories, analog blocks. Proper placements of macro has a great impact on the quality and performance of the SIC design. Micro placements can be manual or automatic. Okay, manual micro placement, it is more efficient when there are a few macros to be placed. manual macros placement is done based on the connectivity informations of macros to input output pins and macro to macro. Okay, as for automatic macro placements, it is more appropriate if the numbers of macro is large. Okay, very critical for congestions and timing. Okay, and result in uniform standard cells area. Okay, this is about a macro block placement. Okay, this block placement determines how the macros can be placed. Okay, and then to use which technique. Okay, they are manual and automatic macro placements. Okay, macro and blocks occupy many area. Okay, occupy a lot of areas, and then if it does not place correctly, okay, it will resulting in the lack of area to place the routing. Okay, so it has to be considered, okay, carefully when we place the macros, okay, or blocks. Okay, if not, it will cause the congestions. Okay, so now I group to different types of macros. Okay, they are hard macros and soft macros. Okay, remember that this macro is actually referred to the blocks. Okay, hard macros means that if the uh, okay, hard macro means that in the circuit, okay, we can see the functionality informations about macros. Only we knows the timing informations. Okay, the circuit is fixed, and for soft macros, the circuit is not fixed, and we can see the functionality and which type of gates are using inside it. Also, we knows the timing informations. Okay, the difference here, as you see from the statements given, okay, it means that soft macros is more flexible, okay, to rearrange, okay, because the circuit is not fixed, okay, and additionally, there are more informations about the functionalities of the macros. Okay, as for the hard macros, the circuit is fixed, and then the informations about the macros we don't know. Okay, only the timing informations is provided. Okay, so this is the difference. And then in placements of the macro, there are some of the guideline here. Okay, you see here in the box here, the macro should be placed near to the boundary or the edges. Macro should be placed according to the hierarchy, okay, sorry, according to the hierarchy. Macro channel space should be proper. Macro pins should be accessible. Macro pins orientation should correct or towards the core. Maximum space for the standard cells and routing. Okay, placements of macros based on the fly lines, it shows the connectivity between macro to macro and macros to pins. So to minimize the interconnects lengths between the input-output pins and other cells. Okay, so this figure shows the placements of macros, okay, based on the fly line. Okay, so for this one, figure A, it is about the placements of macros to the input-output. Okay, since there is only one macros here, okay, and then in between there are the route. Okay, this is routing or routes. Okay, we call them routes for routing. Okay, they are connected using the routes. Okay, from the blocks to the input output pad. Okay, this is actually the pins. Okay. Okay, and then you see that the routes here, there are multiple routes. Okay, these routes, they are uh, called as the fly lines. Okay, uh, fly lines. Okay, you see the label here, they are called as fly lines. Okay, so core area is defined in this area. Okay, another. Okay, this is one of the guideline. This is one of the method of placement, macro placements according to the guideline. Okay, another one is the macro place at the core boundary. Okay, according to the guidelines, the macro has to be placed near to the edges or boundary. Okay, so this one is the cell. Sorry, this one is the macro, not cells. Okay, this one is the macro. It is placed near to the edges or boundary. Okay, if there are more than one macros, okay, this is the uh, placement, macro placements with two macros. Okay, these two macros, they are connected using the routes. Okay, you see the placements here. Okay, two macros here are placed near to the edges, and then it's based on the fly lines. The routings here is connected in the form of fly lines. Okay, and then another one is if we want to reduce the length of the routes, the length of the routes here. Okay, we can place the macros in this way. Okay, macro place near to each other. Okay, and then with the routes. Okay, so this is the about the macro placement. Okay, and it is based on the guideline. Okay, the guideline are stated in the previous slide. Okay, next is about input output pin placement. Okay, input output pins are placed at the boundary of the chip. Its placement is an important step. The placements of input-output pads depends on packaging also. It can be done based on timing, congestions, and utilizations of the chip. Okay, about input-output pin placements, the pins is at the edges, okay, is placed at the edges here, okay. And then when we place the input output pin, okay, we must make sure that the correct timing and less congestions. Okay, to show you the real images of the input output pin placement. Okay, so this is the image. Okay, this is the image. Okay, the image. This is the image that shows the blocks are connected using a bond wire to the pin. Okay, after input output placements, next is about power plannings and routing. Okay, power planning and routing is a step done along with floor planning in order to distribute power with proper power drop analysis across the design so that entire design is getting power uniformly. Okay, this one I need to make a corrections. This is not. This is together is 1 point only. It is called as pre-routing as the power network synthesis is done before actual signal routing and clock routing. Okay, power planning and routing is to distribute the power from power pads to all elements of the chip. Okay, and then unified supplies of power with less voltage drop and a proper voltage, not voltage, proper power design should aim at using as less routing resources as possible. Power analysis check should be done after power planning is completed. Okay, power planning includes proper estimations of power of chip. Power routings the design based on estimations. Okay, we create a mesh kind of structure so that instance can take direct supply from the nearest point. Okay, we create multiples VDD and VSS line for each power domain. Hierarchicals match from upper metal layers to lowest. Connections from highest to adjacent lower metal layer is true, vice. Okay, the figure here shows the power arrangements of the power rings, okay, or power straps. Okay, you see the power rings here, they can be arranged in this way. Okay, these are the power and ground straps that connected to VDD and the ground. Okay, and then this is also the power straps, power and ground straps. Okay, they can be arranged in this way. And for the another one, this is about power mesh. Okay, the power mesh here, there are multiples layers. Okay, upper layers to lower layers according to the statements here. Okay, this is a samples of a power mesh. Okay, according to this figure, as you see that there is a macro. Okay, and then this macro is with power pins. Okay, these pins are connected to the power and the ground. Okay, and then this line here is called the core power ring. Okay, this is the core power ring. And then this one is also the same core power ring. Okay, and then this one, this is also a line. This is a line called as macro power rings. Okay, so for power planning, the core and the macro has its own power ring. Okay, and then all these power rings, they have pins. Okay, the pin is to connect the uh, power rings to the power pads. Okay, this is also the power straps. Okay, the power straps in verticals. And the standard cells power rails. Okay, so this is the standard cell power rails. It's a power rails for standard cells. Okay, so different power rings are, uh, are actually planned for different different elements. Okay, so okay, just now what I mentioned is the elements are the macro, standard cells, and the core. Okay, so each elements they have their own power rings, okay, to connect to the power pads. Okay, and for standard cell, it is called as power rails, okay, not power rings. Okay, power estimations. Okay, power estimation is based on total power consumed by the chip. Okay, it includes the input-output power, core power, and the memory power. Okay, core power consider the combinational logic power, sequentials, and clock power. Okay, so all these have to consider when doing the power estimations. Okay, and where does the all power goes to? Okay, the power supply to the chips should considers to supplies to the standard cells, macros. Okay, all standard cells and macro they are the they consist, okay, they consist of the combinational logic power, not logic power, they consist of combinational logic circuit, sequential circuit, and the clock. Okay, all these circuit they consume power. Okay, so we must make sure that enough there is enough power supplies to the chip. Okay, so this chart shows the total power. Okay, this total power is to estimate from the core, okay, input output, okay, and then in the core, okay, there are standard cells and macros. Okay, these two they consume the power. Okay, above standard cells placement. Okay, standard cells placement. Uh, this is a standard cells placement. Okay, this is a floor plan. Okay, with the input output pins, and in the core here there are macros and also there are standard cells. Okay, and the standard cells here you see, standard cells is with smaller area, occupied smaller area. Okay, they occupy smaller area than the macros. Okay, and then all these cells and macro, they are connected uh, with these routes or the straps. Okay, the straps here are the power straps and the ground straps. Okay, all these can be the routes, okay, or the straps. Okay, so according to this, the diagram here, for standard cells, okay, they are cell 1 and cell 2. Okay, this one, it shows that the connections of the standard cells. Okay, the connections here, as you see, is a little bit different. Okay, except that for VDD, ground, and the clock, okay, they are connected with the same way of the routing. Okay, it means the way how the routes is connects to the VDD, ground, and clock. They are the same. Okay, standard cells have been designed in such a way that power and clock connections run horizontally through the cell, and other input-output leave the cell from the top or bottom side. Okay, about a standard cell space design, okay, this is a floor plan of a standard cell space design. Okay, all these are standard cells. Okay, and then with all the input output pins, we call this as a floor plan. Okay, that has the standard cells. Okay, it consists of two separate blocks and a common signal bus. Okay, it shows that okay, this one is the block. Okay, there are two blocks. Okay, they are divided by a signal bus. Okay, I see that now is almost 3. Okay, we take a break now, 10 minutes break. After that, I will continue with this, the criteria of good floor planning. Okay, let's continue the class. Okay, now that you have learned about micro placement, input output placement, core area estimations, power planning. Okay, now you will see what is the criteria for a good floor planning. Okay, a good floor planning should meet the following constraint. Okay, minimize the total chip area and total length of wire. Make routing phase easy. Improve the performance by reducing the signal delay. Okay, here a figure shows two floor plan. One is a problematic floor plan, another one is better floor plan. Okay, for this problematic floor plan, as you see that the routes here or the stripe, okay, this is the wire. Okay, this is the wire. The blue line is the wire, or we call it as the routes. Okay, you see the arrangement of the wires, and then the length of the wire is long. Okay, the arrangement is still okay. Arrangement still okay, just that the wire length is very long. Okay, if we consider this floor plan with this floor plan. Okay, and for the placements of the macros and standard cells, is also a little bit difference between this floor plan. Okay, for this macro, okay, this is macro, okay, and this is standard cell. Okay, macro is usually with a larger size than the standard cells. Okay, so the placements of these macros is also different. Okay, this one, if we want to make sure that the wire length is minimized, we have to make sure that the macros that are connected to each other must be near. Okay, so for this one, you see that the connections through the wire is long. Okay, when the macro are placed very far from each other. Okay, if to reduce the length of the wire, we can actually place them near to each other. Okay, so this is how we can reduce the utilizations of the area. Okay, a smaller area that are occupied. Okay, if we consider this floor plan as the core area. Okay, and then for standard cell as well, okay, it can be rearranged in a different alignment, okay, or orientations. Okay, and then for this macro, this is also macro. Okay, these arrangements are okay. Okay, except that the wire here, we can rearrange it in this way. Okay, this is about uh, the numbers of wire. Okay, the numbers of wire is minimized. Okay, if we do the comparisons here on this the wire. Okay, so this is the objective that we have to achieve in a good floor planning. Okay, one is to minimize the total chip area. Okay, you have to remember minimize total chip area and total length of wire. Okay, another one is to make the routing phase easy. Okay, means routable. Okay, and also with improved performance. Okay, by reducing signal delay. Okay, signal delay can be reduced in many ways. Okay, one is by reducing the signal wire. Okay, not okay. This one specifically. Okay, I want to mention just now. Okay, this one if to reduce the signal delay. Okay, uh, we can actually reduce the signal wire length. Okay, if we reduce the wire length, means we can reduce the signal length, signal delay. Okay, it can reduce the signal delay. Okay, so let's say if we use this two floor plan to take as an example. Okay, imagine that if there is a signal transmissions through this wire in this floor plan. Okay, and also signal transmissions through the wire in a better floor plan. We can note that the signals, the quality of the signals will be better and faster received at another point. Okay, in this better floor plan. Okay, uh, the quality of the signals is depends on the wire length and also other factors. Okay, so the performance here can can be improved uh, by considering uh, some of the factors here. Okay, performance here like the delay. Okay, the delay and then the power consumptions. Okay, all this we have to consider. Okay, there is another examples here that shows good floor planning and bad floor planning. Okay, this one is an examples that shows the placements of the routings. Okay, or of the routes. Okay, of the routes. Okay, and for a bad placement. Okay, a bad placement as you see that the routes here are all in mass. Okay, and for the good placements in the floor plan, uh, the routes here, as you see that are minimized. Okay, they the amounts of the signal routes that are used in the floor plan are reduced. Okay, in for this one. Okay, so according to the statements here given for the bed placement, okay, it causes routing congestions resulting in increases in circuit area and wiring. Okay, when the utilizations of the circuit area increases, okay, it means that the cost also increase. The cost also increase. Okay, and the longer wire, okay, will cause more capacitance and longer delay and with higher dynamic power dissipations. Okay, so here you can easily see that, okay, all these routes or wires, okay, they are longer. Okay, they are longer, and then this longest wire will cause longer delay. Okay, and then there will be also more capacitance. Okay, and then the power dissipations also higher. Okay, for a good placement, the circuit area and the wiring decreases. Okay, and the use of the shorter wire will have less capacitance. Okay, a shorter wires also will give a shorter delay and less dynamic power dissipations. Okay, so this example shows the importance of the placements of the wires. Okay, so you have to remember this. Okay, you need to do your revisions on this. Okay, if you are still not clear, later on when you study, you need to do you need to try and understand. Okay, uh, the examples given here. Okay, importance of floor planning. Okay, quality of chip design is determined by floor plan. A well-organized floor plan results in a more efficient utilization of the core area, thereby aiding the placements of the standard cells without causing issues related to congestions, timing, signal integrity, and etc. Bad floor plans affects the area, power, reliability, life of the chip, and require more efforts for closure, and it can increase overall IC costs. Okay, so this shows the um, importance of good floor planning. Okay, okay, so this one you also have to remember. Okay, as a summary, macro and pad cells locations are defined during the floor planning stage before the P and R. Okay, P and R, this is means by placements and routes. Okay, this one is placement and routes. Okay, before we do the placements and routes, okay, the locations for the macros and the pad cells have to determine first. And the standard cells are placed in the placement rows during placement. Okay, placement rows are commonly abutted to reduce core area. Cell orientations in abutted rows are normally flipped. Cells in a timing critical path are placed close together to reduce routing related delay. Okay, the circuit delay, power dissipations, and area are the main objective of placements. Okay, routability or congestions is a function of the numbers of available tracks in a given area compared to the numbers of signals that needs to be routed through that area. Okay, routing along the timing critical path is given priority. Create shorter, faster connections nearby, reducing the parasitics. Okay, so this one is the summary. Uh, the the importance of the floor plan as a summarize. Okay, has summarized to you. Okay, so this is the end of these topics. Okay, in chapter 4. Okay. Okay, I see that the times here is still early. Okay. We still have half an hour. Okay. Okay, I have an announcement here about the submissions of the lab report. Okay, I need to inform you which date and day. that you all have to submit the lab report. Okay, so today I will announce the date to you. Okay, the date of the submissions of your report is on Friday next week. Okay, 4th March, 4th of March. Okay, uh by Friday. By Friday means that you can submit during night. Okay, but by before 12 a.m. Okay, so make sure you take note. Okay, I will put the deadline of submissions in Google Classroom as a reminder to all of you. Okay, later I will assign the submissions. So all of you, you must submit your report by Friday. Okay, you can submit the report early. Okay, I will assign the submissions early in this week. Okay, if you have finished your lab report, you want to submit early, you also can submit early. Okay, but latest is by Friday. Okay, please take note. Okay, now let me see. Should I continue? We still have half an hour. Later, 4 o'clock, there is a practical class. Okay, I'm thinking to discuss the tutorial with you. Okay, chapter 5, the lecture notes I have not done updating. Okay, I'm still preparing. I will upload to you later. Okay, I will cover it next week. Okay, since we have half an hour, I'm thinking that whether we should discuss the tutorial 3. Okay, is it tutorial 3 or tutorial 2? Okay, I know that this week, not only this week, last week, okay, for tutorial 3, as I remember, okay, it is about logic to CMOS circuit design. Uh, there is not much time to discuss the solutions during the tutorial. Okay, so I want to make use of this half an hour to discuss some questions. Maybe not enough time to finish all the questions, but I feel like to discuss uh, one or two questions here. Okay, I think I will discuss the question 1C, the solution. Okay, within this half an hour, if I still have time, I will continue with question 3A. Okay, I know that all of you are here. I actually hope to ask you to provide the answer to me so that I can check um, whether you can understand and whether you know how to solve the questions. Okay, will that be okay if I ask one of you to provide me the answer? Or you just prefer me to directly show you the answer and then you can check yourself? Okay, so for question 1C, it's not difficult. It is quite easy. Okay, if you do the revisions and you can understand what is covered in the lecture, okay, you should be able to draw up the schematic diagram as well as the stick diagram. Okay, I think to save time, I will directly show you here. Okay, my answer. Okay, my answer is not the only answer. Okay, they can have a multiple answer. Okay, if you get a different one, if you check my answer with your answer, you get a different answer. Don't worry, you need to recheck. Okay, your answer can be correct. Okay, because the answer is not only one answer. Okay, so for question 1C, draw the minimum CMOS transistor network and stick diagram that implements the functionality of Boolean equations respectively below. Assume both the originals and complemented versions of each literals are available as a gate inputs. Okay, so the questions that I ask you to try is part C, F equals to A bar plus B bar and C. Okay, and the diagram, it should look like this. Okay, the Boolean functions already given here with three transistor, PMOS transistor and NMOS transistor. Okay, so all the input must be right correctly. Okay, so given here, this is A bar plus B bar and end with C. Okay, we need to rewrite it. Okay, with having a bar here. Okay, after we apply the De Morgan's law, okay, the functions can be rewrite with this A and with the B and all with the C bar. Okay, and with a single bar. Okay, we use these Boolean functions and we get the F bar. Okay, F bar will become A, N with the B, and all with the C bar. Okay, then we use these functions. Okay, this one is for the, okay, this one is for NMOS. Okay, and this function is for PMOS. Okay, and then based on the functions given, we can easily know how we should draw the schematic. Okay, through the AND and OR operations. So this is the OR operations. This is AND operations. This is AND operation. Okay, for all operations in the pull down network, it is in parallel configurations. Okay, means that B and C bar will be in parallel. Okay, so you see that this is B and C bar is in parallel, and then A is N with the B and C bar. Okay, N is in series, so A is in series with B and C bar. Okay, so you see this is the configurations in the pull up network. Okay, this is pull up network, this is pull down. Okay, in pull up network, okay, the configurations is in opposite than the is in opposite. Okay, if compare with this pull down network. Okay, in pull up network, you see the configurations here. B and C is in parallel in pull down network, but in pull up network, it is in series. Okay, and then it is in parallel with the transistor with input A. Okay, so the configurations is in opposite. Okay, so in the schematic, you need to make sure that you draw the VDD. Okay, it is connected to the VDD source, the ground, and all the transistor and the output. Okay, and then after you draw the schematic diagram, then you can start to draw the stick diagram. Okay, for this one, the stick diagram that I draw is in this way. Okay, stick diagram can draw in many ways. Okay, in different representations. Okay, but I use this stick diagram and also with the ULIP path. Okay, ULIP path is a method. Okay, this is a method that used to optimize the area of the optimize the diffusions area. Okay, why I say so? Because uh, this method can help us to get a proper order of the polyline. Okay, by having the proper order of the polyline, then the diffusions area can be minimized. Okay, if you cannot understand what I mean here, you need to refer back to the lecture notes. Okay, for this one, um, we can easily identify the ULIP path. Okay, the path can be from A, B, C. This is the path that's through each of the transistor having the input A, B, C bar, or the path that is going through the transistor with input C bar, B, and A. Okay, the stick diagram here, I follow this one. Okay, I follow this one, the ULIP path. Okay, if you use a different path, you get a different ULIP path, then you also can draw the stick diagram. Okay, but you need to make sure that your ULIP path must be one directions. Okay, through each of the transistor in pull up and pull down network. And then the transistors, the sequence, okay, the sequence of the transistor must be the same, okay, in both network. Okay, so for this one, the stick diagram also with a VDD and ground, and this is the P plus diffusion. Okay, this is N plus diffusion. Okay, and then all the connections here with contact must be draw and label. Okay, the connections here, if you want to draw the correct connections, okay, you need to label the source and drain terminal. Okay, these are the steps that you must follow. Okay, all these steps are followed if you draw the stick diagram in this way. Okay, so source and drain terminals must be labeled in the stick diagram so that you can draw the connections to the output and VDD and ground correctly. Okay, so for this one, okay, since we all know that source terminals of the PMOS are connected to the VDD, so we can put connections here, okay, A and B. Okay, if I follow my stick diagram here, okay, A and B, according to the schematic, the source terminals, its transistor is connected to the VDD. Okay, so we can actually put connections here, okay, that connects the terminal source terminals of the two transistors to the VDD. Okay, if you ask me why cannot put here, if I put the connections here, and then the connections of the source terminals to the VDD will be difficult, okay, to connect. Okay, it will be incorrect. Okay, it will be incorrect because if you put this as a source terminal, this is drain terminals, then the connection is not correct anymore. Okay, so we want to optimize the use of the contact, and also we want to minimize the signal routings or the wire. We can actually put them together at the same terminals, means only same wire to the same terminals for both transistor. So the source terminals here, we can label it both here and to the same point, which is to the VDD. Okay, so and then for others terminals, we can label subsequently. Okay, we know, okay, if this is source terminals, and then this is, of course, is the drain terminals, and this is also drain terminal. Okay, and this is a transistor with input B. Okay, and this is connected to the source terminals of the transistor with input C bar. So it means that this point, okay, they are in series. So straight away we can label this as the source terminal. Okay, this is in series. Okay, and then this is the drain terminal. Okay, drain terminal of the transistor with C bar. Okay, these drain terminals will be connected to output. Okay, and not only the source and not only the drain terminals of the transistor with input C bar, it is also the drain terminal uh, of the transistor with input A. Okay, means this point, this part at this part. Okay, so at this point, both are connected to the output F. Okay, so this is the connections to output F. Okay, the output here is F. You need to make sure that the output label is according to this output in the schematic. Okay, for the pull down network, also the same. The source is connected to the ground. Okay, so we can easily identify which one is the terminals in the stick diagram. We can label ourselves. Okay, which one we can label and determine. Okay, okay. So for this one, this is a source terminal. These two terminals are connected to the ground. okay, with a contact. Okay, and then for others, like this is the drain terminal. Okay, this is drain terminal, drain terminal. Okay, we can then label accordingly. Okay, so for all the drain terminal, it is all the drain terminals of the transistor with input B and C bar. Okay, they are connected to the source terminals of the transistor with input A. Okay, so you see that this is the source terminals of the transistor with input A. Okay, they are connected. Okay, make sure that um, these connections are connected. Okay, there must be a wire with contact. Okay, for any point, for any terminals that are connected together. Okay, for this case, okay, here there are three terminals. Okay, three terminals here. So if we want to connect these two terminals to another one terminal, okay, we need to use a wire to connect it together. Else, it will be incorrect. Okay, and then for the drain, this is the drain terminals of the transistors with input A. Okay, it must be connected to the output F. Okay, so this is the point where it indicate here. Okay, so the connections here is not difficult. After you understand this, then you will be able to draw the complicated circuit. Okay. So if for other stick diagram with others unit path, the connections here, of course, will also change. Okay, I assume that all of you have no issue for now. Okay, maybe some of you didn't listen. Okay, but it's okay. Okay, make sure that later you do the revisions, you try to understand, okay, what is meant by the stick diagram here given. Okay, for this tutorial, I will upload the solutions to you, not all, only for certain questions. Okay, I will upload the solutions to you later. Okay, for other questions that I ask you to solve, I will discuss with you in the next class. Okay, I see that I don't have much time now. Okay, uh, okay, let me check your attendance. Okay, the attendance form I received is 28, but according to the list that I have in Google Meet now, there are only 27, excluding me, and also Soyan Chan. There are two. Okay, two students have not two students. Okay, one student I see that with two cow. Okay, so here is having a 27. Okay, currently I didn't manage to find out who is the one. Yeah, I don't know who has left. Okay, but it's okay. I will recheck back. I still have another record. I will check that record. Okay, I think no problem. Okay, we can dismiss class now. Thank you. For the next class, group 2, please stay back. There is another practical class today.